SMJP 1022 Material Science Chapter 5 Dislocation and Metal Strengthening Mechanism. In this chapter, we will divide it into three parts. Part A, which is material deformation. Part B, metal strengthening. And finally, Part C is a cold working and hot working. In this video, we will cover into Part A, which is material deformation. In Part A, we will cover deformation, elastic and plastic deformation, slip and twinning deformation, and finally, dislocation. Deformation is the changing of shape of metal under the action of force. It will give a desired shape. Metal deformation is more superior than casting metal. Casting metal we have learned in previous chapter. Which is shown in this figure. Operation of deformation can be done by rolling, forging, extrusion, spinning, and many more. Material may experience two kinds of deformation. The first one is elastic deformation, and the second one is plastic deformation. The graph can be seen through the stress-strain curve. Elastic deformation, defined as a process of deformation which is non-permanent, which appear and disappear with the application and removal of stress, which is it can spring back to original position. Process at the beginning of the deformation progress. Over the short range of stress-strain curve. When stress is applied, displacement of the atom from original position. When stress is removed, atom spring back to original position. Whereas for the plastic deformation, defined as a process of permanent deformation and exists after removal of stress. Process takes place after elastic deformation has stopped. Over the wide range of stress-strain curve. When stress is applied, corresponds to movement of many atoms. When stress is removed, atoms stay at its last position, which is a permanent deformation. Here is the initial state of atomic arrangement at a particular rod. Under the elastic deformation, we can see if the small load is applied, the elastic deformation takes place, which is bond stretch. After the force is released, it will spring back to the original position. For the plastic deformation, the original position at a particular rod is something like this. When applied load, it will stretch the bond and plane shear. We can see the rod is extend at a certain length. When unload is applied, plane still at shear position, whereas the plastic deformation, there is no spring back to the original position. It will stick at the certain length from the original position. Plastic deformation may occur under tensile, compressive, shear, which is the function of stress, temperature, and strain rates. There are two basic models for the plastic deformation. The first one is slip deformation. The second one is twinning deformation. In slip deformation, this is due to sliding atom planes over the others. Crystal orientation above and below slip plane is the same after deformation. Atom movements are over large distance, required lower stress for atomic movement, occurs on widely spaced plane. And this is the diagram of slip in plastic deformation after the applied force. We can see a adjacent plane of a crystal. Shear stress move upper plane's atom to the right. Movement occur when shear stress exceeds critical value. Atom move a number of atoms distant. You can see from the figures below. Stress applied and elastic strain produced. Stress applied and yielding occurring, and finally remove, leaving permanent deformation. And we can see a produced step, and slip plane is along the way in the red line. Here is the figure shows the process of moving of atom and finally produce a slip step. Here is the diagram shows in 3D, whereas atom move and finally the slip planes produce the direction of dislocation movement to the right. Here we can see that the atomic movement we will produce the dislocation movement, or we call it dislocation motion. This is the micrographic of by using scanning electron microscope or SEM to indicate that the step produced in sleep deformation, and the left hand side is the schematic diagram of atomic arrangement of sleep deformation and the sleep direction after apply of load. And then we go for twinning in plastic deformation. This is due to change of orientation of a crystal with others. Here you can see a diagram shows the different set of atomic arrangement after the applied force. We can see a twinning direction. Twin portion is the mirror image of the original lattice. Atomic movements are over a fraction of atomic space, required higher stress for atomic movement. Occurs on every atomic planes involved in twinning region. Here is a schematic diagram of atoms arrangement before and after the applied force. And finally, it will produce a twinning in plastic deformation. Deformation twinning is described by the twinning plane and a twinning direction. As you can see, two parallel lines in red color indicates the twin planes, or other words, they call it mirror planes, and a twinning direction at the bottom. This area basically set as a twinning region. This area. Atoms move in the twinning direction by a displacement generating twin shear. The twin structure is a mirror image of the parent structure about the twin planes. We can see here is a twin planes or mirror planes, and right hand side is a parent structure or original atomic arrangement before, and this area is a mirror image of this structure, whereby this line is a twin plane or mirror plane. The distance move in such that a fully coherent boundary is formed. That is, each atom is in the correct position related to the original system and the twin lattice. Metal usually deform by twinning when it unable to sleep. Twinning produced by shear stress, known as mechanical twins, occur in BCC and HCP metals at low temperature and high rate of loading. Annealing can produce annealing twins occur in certain FCC metal, especially for copper and Ag. This is the scan picture of scanning electron micrograph, or SEM, indicates a twins at this area, and we can see also a sleep together as this area. Finally, in dislocation, which is a plastic deformation correspond to motion of dislocation. Plastic deformation occurs when large number of dislocation move and multiply so as to result in microscopic deformation. In other words, it is the movement of dislocation, or we call it dislocation motion, in the material which allow for deformation. Dislocation is a linear disturbance of the atomic arrangement, may occur during solidification. The motion is called slip and can move easily on slip planes. Movement can be stopped by boundaries, act as a barrier or obstacle, have tendency to multiply during deformation. Two types of dislocation. The first one is edge dislocation and second one is screw dislocation. Here is the diagram of edge and screw dislocation. Basically, edge and screw dislocation have learned in the previous chapter. So in this chapter, we just highlight about the dislocation consists of edge and screw dislocation in terms of dislocation movement. So in this slide, we just highlight about it. And if you want to learn more about this edge and screw dislocation, please refer to the previous chapter. Thank you very much. Bye bye.